Here we are now. I welcome you now to the next session. Our session this time around is just talking about welded joints. You noticed in the previous session, we're talking about riveting two materials, riveting two joints, riveting two pieces of metal together to make a joint. What if you decide to weld those joints? So our focus will be to design such a weld, or rather to come up with a joint that is welded. And what we are going to do is to come up with the size of the weld so that you can guide the person who is doing the weld to say, we need maybe electrodes that are supposed to be used of this size. It will come from the calculations that we're going to do. But before that, we'll need to explore some principles under welded joints. So before, like I've said, exploring the principles, here we will come to the advantages of welded joints. Now, what I want you to have in mind is, what if you're comparing this with those riveted joints? First thing that will come to mind is that a riveted joint, you cannot compare it to a professionally welded joint. Their efficiencies are higher. And if you look at the way we're talking about riveting materials together, we overlap. We put a plate to make sure that a hole can run through the next one so that material is joined together. That adds to the weight. But in case of welding, the welded joints end up being lighter because you're just bringing the materials together, then you weld in between, fuse the material in between, and then you proceed. And in the end, these are also stronger. If you want to modify a welded joint, it can be easier to do even in an existing joint because you will just unweld it, and then later on you start making your modifications that you need, and then you proceed. Now, in riveted joints, members that are in tension end up being weakened, not with welded joints. That is their strength. If you want a rigid joint, go for welding that joint. Then it will end up being rigid and sturdy. Then welding, you just bring the two materials together, connect your equipment, and start welding. With riveting, you should determine where the rivets are going to be, drill the holes. In fact, we're saying, first of all, do the marking out and the measurement, then you mark out, do the punching, the centers, drill out the holes, then punch those holes in the various centers. Then after that, you can now bring your rivets and your riveting gun or your riveter. If you're using a machine, that's it. Then you start riveting. That's a lot of time. In welding, we just proceed. So there's no need for that. And of course, the smaller sections can be used as compared to the riveted ones. Then even the outlook, if you look at a welded joint, it looks smooth and appealing. The surface finish is quite proficient and quite more appealing compared to a riveted joint. The bad side, welding is not a skill that you can just go to the road and pick anyone to do it. Riveting, as long as you've done a good job with drilling and punching in the right places, anyone can come and rivet your joints. It's not one that always requires skilled manpower. And when you look at welding itself, along the way, it distorts the members because you're talking about melting the materials that are involved, fusing them together. Then also, inspecting those joints can be difficult as compared to riveted joints. Then also during welding, you have cracks that will be formed. Sometimes you also have stresses forming as a result of that. And remember also, the equipment you're going to use is expensive. And it's not one that you can just easily connect. It has parameters that you need to use as you do the connection. So equipment is more expensive as compared to the riveting, which is relatively quite affordable and easier to organize. When you are welding, you need Good PPE that will protect your respiratory system, because the fumes that come from there are they pollute the environment. Even the light coming from the place where you're doing the welding can also be dangerous to your sight or to your eyes. Here we're talking about the same flames. So it is a health hazard. Welding can be so dangerous as compared to riveting in those areas. Types of welds, we have butt welds. A butt weld, like we had mentioned, is where we bring the two ends of the materials together. Then perhaps we may do some mini grinding, and then we start welding the materials so that they can be properly fused together, making different shapes as you do that. In a lap joint, you have one material overlaying the other on top, then they overlap. Then you can weld at the end where they are meeting like this. So in this case, you may have this as your weld, and then your material there, that is in where you have welded it. Everything has been welded. But when we're doing the analysis, we're basically going to consider this like basically like a triangle, because that makes our analysis more professional and giving us the results that we're looking for. So this is one member on top, and this is the other member, and we're joining them together. So what happens here is that with this, you just draw a line. This is your weld. This is where you were doing the welding. Then you have this line across. This line which is cutting across is the one we call the throat. The throat represents the strength of your weld. If this is distorted, or if your weld is going to fail, it means this has been weakened and it goes away. And then the height of your weld represents what we're going to call the leg. So if we say, give us a 10 millimeter welding rod, we're basically asking that when you weld, because that's what is going to guide the height of your weld, it is going to be that height. So that's the one we'll be calling the leg. From this, you can already see that the angle here is 45, just like there. So extracting this small triangle here, you will notice that T is opposite 45 degrees. So I can have T over, because this is the leg, T divided by leg already gives me sine 45. So I'm saying that sine 45 is equal to T over the height of your weld or the size of your weld as leg. So why not make T the subject? So if I make T the subject, I just cross multiply. And hence I have T equals leg sine 45. So here I'm basically just multiplying. Let me go through that again. What we're saying is that the height of your weld is the same as this, and we're calling it as leg. If you go to the principles that you got from SOHCAHTOA, an angle that you find by the two sides where the hypotenuse, rather the opposite as well as the adjacent are the same, it's 45. So that's why you can say tan inverse of 1 is 45. Now of interest, because this is the weld that you are putting as you continue fusing together this material to the other. In 3D, that's how things are. And then that is your weld going there all the way there to the other end. Now this T, considering this as your mini triangle, you have 45 in the corner. This is T, which is opposite the angle. Then this is leg, which is representing the hypotenuse. So T divided by the hypotenuse, T is opposite 45. So opposite over hypotenuse, it gives us a ratio which is sine, and our angle is 45. But because we want to get rid of, we want to make this, calculate for this, we say T equals, we cross multiply. leg multiplied by sine 45. So that's why we have leg times sine 45. We know sine 45 is 0.7071 and so forth. So that's why we can leave it like that. Or I usually recommend leaving it in this format so that you have something more accurate. Let's do some application. We have a plate 40 millimeters wide, carrying a load of 100 kilonewtons to be welded by 4 equal fillets to another plate as the diagram is showing. Now, here I must emphasize that there was another part here which is supposed to also have 40 millimeters. So this is 40 millimeters. That's 40 millimeters. Now, the force that is acting on these welds is 100 kilonewtons. What is our task? We need to calculate the required size. What weld size are we going to put there so that this force cannot pull out this member from where it has been attached? That's our task. Then in that case, let's go then to our work. We have the effective area. The effective area of the material is supposed to be the length multiplied by the throat. The throat is T. The length is that, which is 0.04. Why is 0.04? Because they are having the same length both for the end fillets and also for the side fillets. The dimensions are the same. So hence we've used 0.04 for each of those characters. So that is where we are. Now let's just try to finish this up because we want to find the load carried by the side fillets. If I take you back here, you'll notice that these are the ones we are calling the end fillets. Then on the sides here, the top and up and below here and up there, those are your side fillets. These are the end fillets. But in this case, they are quite, their lengths are the same. So it can be easy to confuse. But what will help us is that we've said that the side fillets are carrying stresses of 70 meganewtons. Then the others, we're saying that the other one for the end fillets is 100. So we're going to start with the side fillets then. So for the side fillets, this being the area, we're multiplying the throat by the length, which is 40 millimeters, ending up as 0.04. This gives us the area. To get a force, we multiply stress by area. Because if you look at the definition of a stress, stress is force over area. If stress is force over area, then you can make force the subject of the formula, meaning you just do the cross multiplication where you say stress times area, stress A. And so this is now the effective area, which will now give me effective area 0.04. This is for the side fillets. The question is, how many side fillets do we have? There are just 2. So 2, what is the stress acting in the side fillets? 70 meganewtons. So 70 times 10 power 6. Then this, you can now multiply it by the area, which is 0.04. What do I have? 5.6 million. T. We still have the T hanging there. Can I do the same also for the end fillets? Correct. So 2 times the stress in the end fillets times the effective area. So 2, the stress in the end fillets is 100,000. The dimensions were basically the same. So the area is also 0.04 T for the end fillets. So here I have it, 0.04 T times the stress in the end fillets, which is 100 by 10 power 6. Everything multiplied by 2. What is my result? 8 million T. These numbers look scary, isn't it? But even if they look scary, they will basically melt down to something simpler and you'll be able to enjoy the result, because we just want to know the size of the weld. How how much of the welding rods should we use? What size of the welding rods are we supposed to use here? So what we do next is to realize that this load on the side fillets combined with the load on the end fillets gives us the total capacity of this weld. Because this is what is now on that one, on that material that we're dealing with. So in this case, what we are going to do is to add these two numbers, this and that. So 5, 6, and then 8. 5.6 million or 5,600,000 plus 8 million TT. All of them are having the T's. The result is 13,600,000 T. Are we done? Let's get to the first part. I mean, the last part. Here, the T is hiding what we're looking for. So what I will do now is that this being the capacity of the welds, I also have the load acting on the material. So what I'm going to do is to recall this load, which is 100,000, and equate it to what these welds are supposed to handle. So 13,600,000 T equals the load on the material, which is 100,000. So let me divide both sides by this 13,600,000. Even here, I divide by the same number. My answer will be T equals 0.007353. Let's go back where we're coming from. What did we say about this? We had this where we said T equals leg sine 45 by standard, by the nature of this fillet we're drawing or we are welding, unless special conditions have been provided that perhaps someone was doing a special weld which comes with a very funny shape as it is filling into the metal there, trying to make a joint. But in this case, things are straight to the point. So here I recall the formula, which was T is leg sine 45. And I'm looking for the leg, which is the size of the weld. Make it the subject of the formula. I'll have leg is equal to T divided by sine 45. So then my T is this number I have here, 0.007353 divided by sine 45. When I do that, my answer is 0.0104. This is in meters. This is in meters. Suppose the question is asking you to convert this to millimeters. You get that answer multiplied by 1,000 and you get it as 10.4 millimeters. Again, my emphasis is you can be intelligent, wonderful, good enough. You are a mathematician, congratulations. But when you get your final answer like that, and there are no special conditions attached, leave it like that. This is your final answer. If the question was pushing you to convert your answer, put your answer in meters, or we are saying that traditionally these welds, the weld size is supposed to be in millimeters, then you can do that. But for now, leave it in meters like that. You're okay. There's no stress about it. Here's our second example, last example. So we have this special shape you are seeing here, which has 6 welds. 1, 2, 3, and 4. These are all diagonal welds. Then we have 1 and 2. These vertical welds are actually on, we can say like they are behaving like end fillets. So we are calling them end fillets. By inspection, you can already see that the length of this end fillet is simply 50 millimeters. Do I know the length of this diagonal fillet? I don't know it. What am I supposed to do? I can use Pythagoras theorem because I know this length. I also know this length. With that in mind, let's fish out information provided in this question. Here we're told we have a weld provided to connect 2 tie bars 150 by 10. This is what we are connecting together. So this area, the dimensions we have here have nothing to do with the weld that we are going to do. This is for the material, and we're going to use it to reveal the load we're dealing with. Then the stress in the bar is that. Then we also have the stresses that each of the welds are going to be subjected to. So let's get to the data. Cross-section area of the bar, 0.15 by 0.01, because it's 150 by 10 millimeters. Then the product is 0.0015. Stress of the bar, what is the stress in the bar? It is 120 by 10 power 6 because it's 120 newtons per square millimeter. The conversion gives us that. Leg size, we've already told that the weld is 12 millimeters, so we convert to 0.012. When you divide 12 by 1000, that's what you get. Throat, by tradition, it's leg sine 45. Since we already have the leg, we would replace it, 0.012 sine 45. So I have 8.485 multiplied by 10 raised to the power negative 3 in meters. I talked about the diagonal fillets. There are 4 of them. The length of each diagonal fillet is not known. So we use Pythagoras theorem to arrive at them because by they were having the vertical and the horizontal sides like that meeting at 90 degrees. So we can apply this. 0.05 by 0.05, multiply everything by 4. After getting what is under the root, we get 0.2828. The end fillets, we simply say their lengths as 50 millimeters, so 0.05 by 2, giving us 0.1. Then the working stress in the end fillets is 102.5. For the diagonal fillets is 70 by 10 power 6. What is the maximum force in the tie bar? The load. We multiply the stress, which was 120 by 10 power 6, by the area of that bar, which is 0.0015. The answer you get is 180,000. Then let's pick the 2 welds. The first one is the diagonal, the end fillets. The end fillets were under a stress of 102.5 by 10 power 6. Length of the end fillets is 0.1. The throat is 8.485 times 10 raised to the power negative 3. Then the load in the end fillets is 86,971.25. From there, I go to the diagonal fillets. The diagonal fillets, first the stress was 70 by 10 power 6. The length of the diagonal fillets to total length was 0.2828. The throat, in fact, the throat is the same, just like what we have there, is 8.485 times 10 power negative 3. From here, when you enter all this in your calculator, you end up with 167,974.63. Now, here I'm going to get the total load. I'm going to add this for the diagonal fillets. I'll add it to the one for the end fillets. So I add 86,971.25 to 167,974.63. I get 254,945.88. What is this number representing? This is the capacity of the welds. This is the strength of the welds. What load am I having on this material? It's 180,000 newtons. The question was simply asking us to investigate the weld. Tell us, is this weld safe? Looking at the way the material has been loaded, are we safe? Are we recommending that perhaps we increase the size of the weld, or are we okay leaving it the way it is? So considering the way things are, the welds are able to handle 254,945. And yet, the load that these welds have been given is simply 180,000, which is very small. So with that, we're saying that the strength of these welds is higher than the applied load. Hence, the weld can withstand the load. It's safe. This weld is safe. We've done our investigation of the load of the joint. This is how you analyze the welds, and I expect you also to attempt these questions in the exercise and see how you fare. Once again, feel free to get back to me where you feel there's something needing clarity. Get on the comment section or reach out to me. I'll definitely find time to quickly respond. So we end here, and next we'll look at failure analysis.